everybody. We are now recording, test recording number 1. Okay? You may notice as you're watching at home or as you're watching here in class, the cursor flashes while I'm recording, so that may drive some of you crazy, but sorry, just how it goes. Alright, I want to do the first section. I wanted to go over questions number 5 and number 6 with you, because, actually, we'll go, questions 5 and 6. Because I find that questions 5 and 6 are ones that people have trouble with because of where the variable is that you're trying to solve. So if we take a look at number 5, okay, we'll get number 5 on its own page here. There's number 5. Okay. Make it a little bigger. So, problem with number 5 is what? Where is the variable that we're trying to isolate by itself? It's where in this fraction? It's in the denominator, right? I find that people have trouble with this for whatever reason. Okay? If we're trying to solve for something that's in the denominator. This one is set up in a way that you can do it in one of two ways. This is how I choose to do it. Mathematically, I really don't care how you choose to do it, but this is what I'm thinking when I see this. Okay? If I have two fractions here, right? Fraction equal fraction. Mathematically, what can I do there? Cross multiply. That's what I think to do first. Okay? So, if I cross multiply here, like this, I end up with 6.8 times 1. You don't have to show me all these steps. I'm just showing you this is the first time we've done this. Okay? Equals 4.3x. I think we can probably handle it from this point, right? Okay? Divide by 4.3, divide by 4.3, you end up with x equals, I don't know, 1.2-ish or something like that. What is it? 1.58? Like that. Problems there? The other way that you could do this problem, here, we're trying to get x out of the bottom of this fraction and bring it up to the top. So one way we can do that is if I take and I multiply this side by x. If I multiply this side of the equation by x, what happens to my x's here? They cancel. But if I multiply this side of the equation by x, I got to multiply this side of the equation by x. And when I do that, I end up with 4.3x over 6.8. But that doesn't get rid of my other side of the equation. What happened to everything over here on the left? Mathematically, it all did what? It all just canceled out. So if everything cancels out over here, what's left on the left-hand side? Or what remains on the left-hand side? Just 1. Can we take it from there? I hope we can. Okay. Good there? The other one, similar, is number 6. Number 6 looks like this. Again, two fractions equal to one another. Mathematically, to me, the first thing I think of at this point is to do what? I cross multiply. That's how I solve this problem. Boom, boom. 0.57 x squared is equal to 0.22. Okay. I think you probably can take it from here. Divide by 0.57, right? Divide both sides by 0.57, and you end up with x squared. X squared is equal to around 0.3, a little bit more than 0.3, something like that. Anybody? What is it? 0.385. Okay. And then, to get x by itself, we have to do one more step, right? Take the square root. If I take the square root of one side, I got to take the square root of the other side. One thing to keep in mind, right? If I'm taking the square root of this problem, how many answers do I end up with? I end up with 2, right? A positive root and a negative root. And so, whatever your calculator gives you for the square root of 0.385, technically the answer to that problem is positive or negative. Good there? What is this? Just so we Alright, question questions on those? Okay. Before I turn you loose on the next set of problems, if you notice on the sheet, the next section deals with right triangles, yes? Let's just review some right triangle trig real quickly. Alright. Please don't think that I'm insulting your intelligence as I ask you these questions. I just want to make sure that we're all on the same page and we know what we're talking about. Okay? First, the fact that this is a right triangle means what? It has a 90-degree angle in it, right? That's going to be this one right here. Okay? And because it has a 90-degree angle in it, that means that there are certain relationships between the sides and the other angles of the triangle. I'm going to use a couple of different colors. I'm going to call this angle theta. I'm going to make it red theta. Okay? Theta is just a Greek letter. It's a circle with a line through it. You'll see it a lot throughout this year. This one down here, I'll call purple theta. Okay? Just different colors. I know it doesn't make, but I have different colors, so just use different colors. Okay? When it's all said and done, what does this angle plus purple theta plus red theta have to equal up to? 180, right? All the angles of the triangle got to add up to 180. This side, right here, the side across the triangle from the right angle, also the longest side of that triangle, we refer to as the hypotenuse, right? It's always the longest side of that triangle. Let's call it hypotenuse. Okay. Then, the other two sides, we label as something different depending on which angle we're dealing with, right? As far as the red angle is concerned, if we go across the triangle, right, that would make this side the opposite side of the triangle in relation to the red theta. And that would make this side here the adjacent side in relation to that red theta. Yes? Okay? But as far as the purple one is concerned, right, this one is the opposite side in relation to the purple triangle, this one being the adjacent side. Good there, right? Hopefully that's good, all sounds familiar, right? The reason why we have to identify these sides and everything like that is because we have our three trigonometric relationships that relate the angles and the sides of these different triangles as we go along, right? Are we all familiar with SOHCAHTOA? Right? I guess some teachers teach it, some teachers don't. Especially if you come from a different school. Does anyone not know what I mean when I talk about SOHCAHTOA? Raise your hand. Okay. Just a way of remembering our different relationships of sine, cosine, and tangent. Okay? The one thing that you might run into as we come along here, okay? Let's take tangent for example. Right? There's TOA, right? Tangent is equal to opposite over adjacent, right? The only thing that you might run into here is if you have to solve for theta, right? If you're trying to solve for one of the actual angles in that triangle. Does anybody remember how we get theta by itself on that side of the triangle there? Tangent, or the inverse tangent, depending on how you say it, kind of the same thing, right? So if you have this, right? If we take tangent to the -1 of tangent theta, which is how your calculator writes it, tangent to the -1, these two things will cancel, and you'll be left with just theta on the left-hand side. But if you take the inverse tangent, tangent to the -1 of the one side of the equation, you got to do it on the other side of the equation as well. So we can solve for the actual angle by taking the inverse tangent of whatever opposite over adjacent turns out to be. Generally, opposite over adjacent is just going to be a number. So you plug that into your calculator, you take the inverse tangent, and that will give you theta. Okay? Before I turn you loose on these problems, and a lot of you are doing them already, and that's perfectly fine. One reminder, you want to have your calculator in degrees. Okay, so you want to check your mode and make sure that you're in degrees as far as that goes. So when you're taking sines and cosines and tangents, that will make a difference. Okay? For now, why don't you do 2 of the 4 triangles that are on that page? If you finish up 2 of the 4 triangles, you can go ahead and move on to the next part. I'll give you a couple minutes to work on that. Then we'll come back and we'll talk about other parts of the backside. Okay? I'll put answers up here on the board. You can check along as check them as you're going along. We'll come back in a little bit. If you want to work with somebody, please feel free to do so. All right, everybody, back recording. If you would please, flip that sheet over to the back side. Let's turn our attention to the graph that's on the back side. Over on the left, it says the figure to the right shows the graph of the time required to stop a lab cart moving at various speeds. Use this graph to answer the next 3 questions. The reason I do this is because you'll see this kind of setup show up a lot on tests. Here's a picture. Use this picture to answer the next couple of questions. So, let's talk about question number 9. What is the value of the slope of the above graph? So, back in Algebra 1, you learned how to define the slope of a line. How do we define the slope of a line? Rise over run, right? So, slope is equal to rise over run. So if we take a look at this graph, right, let's just go, and it's got the speeds on the left-hand side, it's got the time on the right, or on the x-axis. So if we just take a quick little look here, okay, if we go up the y-axis to 1 second, if we rise 1 second, and then we run across to where it hits the graph, nope, that's not straight. If we run across where it hits the graph, right, we should see that it should intersect right around 4 seconds. Is that correct? Okay. So if we go up 1 and over 4, that means the value of that slope is equal to what? 0.25. It's rise of 1 over run of 4. Okay? Everybody get that? Next, what would be the correct units on the slope of the graph? So let's talk about that. Okay? In math class, really you're just making this picture and it's a bunch of numbers, really doesn't mean anything. But here, this is a graph that we made of actual measurements that were taken in a lab setting. So yeah, the graph tells us something, but we can also imply some information that maybe isn't like directly apparent from looking at the picture. So we just have already established the fact that slope is equal to rise over run. If we look at our graph, what are we measuring on the rise axis? What's the rise axis labeled as? It's labeled as speed unit-wise. That's going to be meters per second, right? So that means that if we look at just the slope here, and just from a unit standpoint, we have meters per second on the top of that fraction of rise over run. What are we measuring on the run axis? We're measuring time, and that gets measured in seconds, right? So now we have meters per second over seconds. We have a complex fraction. Let me rewrite that complex fraction to look like this. Okay? Various ways you can go about doing this, but to simplify this complex fraction into something that's a little bit more in line with what we're doing here, okay? To get the seconds out of the bottom here, I can multiply the bottom of this fraction by 1 over s. That would let my seconds cancel. But if I multiply the bottom of that fraction by 1 over s, what do I have to do to the top? I also have to multiply it by 1 over s. Now, on the top of this complex fraction, well, on the bottom, what happened to everything on the bottom? It just all canceled, so we're good with that. It's equal to 1. But on the top, now I have 2 fractions that I'm multiplying here, right? So when you have 2 fractions, we just multiply straight across, yes? Okay? So you end up with meters times 1 over seconds times seconds. See where I got that? Okay? If we multiply or simplify that down, we end up with meters over seconds squared. Good with that? All right, number 11. 11, there's a couple ways you can do this. Okay? I'm going to attack it from a mathematical standpoint. You can also just attack it from a logic standpoint if you want to, but I'm going to go math. Okay? This is a straight line. Back in Algebra 1, you learned the general equation for a straight line, yes? What does the general equation for a straight line look like? Word of it. Y equals mx plus b, right? We call it slope-intercept form. Okay? That's the case with this straight line as well. Okay? Now, let's take a look at this straight line in particular. First, what does the m stand for in y equals mx plus b? Slope, right? It's slope-intercept form. Do we know the slope of this line? Right? We already figured that one out. So we can plug in 0.25 right here. What did the b stand for? Y-intercept. Where is this graph intersecting the y-intercept, or where is the graph intersecting the y-axis? Well, it runs right through which point on the graph? 0, 0, right? So that means that b is equal to 0, because that's where it hits the y-axis. Okay. Y and x are the variables that we're measuring here. What is the y-axis representing? What are we measuring on the y-axis right here? Initial speed, right? So we can change this to look something like this. We'll call this speed is equal to 0.25, because that's the slope. And then what are we measuring on the x-axis? Time. So we can call that, instead of x, we'll just call it t. It's time, right? Plus b, which just happens to be what? 0. What is question number 11 asking you for? It's asking you for a what? If it says, right, how much time, it's asking you for a time. So what does it want you to solve this equation for? T. Did it give you S? It did, right? It said initially moving at 10 meters per second. So if we apply this equation, right, to this problem, we plug in 10 for the speed, and we solve for t. Which should be pretty easy. And when you do, you should get 4. Good there? Questions? Okay. Because our time is running a little bit short here, I wanted to run through one more thing with you, because I find that on the summer packet, it doesn't make a whole lot of sense to a lot of people. So let's take some time and talk about it. Let's take a look at number 13. In number 13, we are going to need this part. Okay, let me go back here real quick. All right. Here's number 13. Number 13 asks you to perform a unit analysis on this equation. So, unit analysis. As far as an equation goes, what has to be true about the two sides of an equation? They have to equal each other, right? That's the gist of an equation. Okay? With that being said, that's true from a numbers standpoint, but it's also true from a unit standpoint. If this is going to be a valid equation, the units that we end up with on the left have to equal the units that we end up with on the right. So, let's start plugging some things in. First, VF. It tells you up here that we measure VF in meters per second. So in this equation down here, no numbers, all I'm going to do is plug in M over S here, where it says VF. Okay? That equals VI, right? So I look up here at the top, VI is also measured in meters per second. So I'm going to plug that in where it says VI. plus. That's just part of the equation. Okay. Next, A, acceleration. I look up here, and acceleration is measured in meters per second squared. So where it says A in this, I'm going to plug in meters over second squared. Everyone see what I'm doing so far? Okay? I'm just looking at units, nothing else. And then the last one, T, okay? T standing for time, right? T is measured in seconds. So I'm going to put that here on the end for T, but mathematically, what does it say we're doing to T in this equation? You're squaring it. Everyone see where I got this from? Yes? Now let's do a little simplification. This one we're not going to touch right now. Let's worry about this part over here. Okay? What's going to happen when I do all the math that I need to do here? Anyone see intuitively what's going to happen when I do all this math I have to do here? The seconds, not just the seconds, but also the seconds squared are going to cancel out, right? I got seconds squared on the bottom here, right? I'm squaring this second to make it second squared, but it's on top of the equation, right? So all I'm going to be left with over there in that whole expression is what? Just m, right? Okay. Plus, not doing anything here. This is meters over seconds, right? And then we're not doing anything here. This is meters over seconds. If I take a look at this side of the equation, can I add meters over seconds plus meters? Can I do that? Okay. Now mathematically, if you have you can't add variables like that, right? If I have x over y plus z, I can't just combine them all together. This doesn't work. Okay. Over here on the left-hand side, I can't simplify the right-hand side any further than that. Over on the left-hand side, though, what's the only thing I'm left with? Meters per second. Do the units match up on the two sides of this equation? They do not. So this is not a valid expression. Okay. All right. From there, if you go back to the calendar, on today's date of the calendar, right, you will see that in the homework section, there is a link that says Answers to Math Review Worksheet. And it has all the answers to all the problems of that sheet, the ones we did in class and the ones we didn't do in class. Practice for you. I already mentioned that up here, there are links to the answers to all the summer packet problems. So you can check those out. Right here in the middle, it says class recording from 5-6 period. That's where I will put the link. So if you want to go back and listen to some things that we talked about in class again, it will be there for you. You can click on the link. It'll take you to YouTube. It'll be fun. Question?